So first, a couple schedule notes. I'm in the class schedule. You'll see a link here. And Nicholas did a really nice exercise. This is a calendar invite if you use an ICS compatible calendar, which most of them are. If you import the calendar invite, it should automatically adjust to the correct time zone. And then the other note is time zone converter. This is the time zone converter we showed at the beginning. I'll show again. This is what I use to plan to track time zone conversion. And so you can use this to check the daylight savings time. And in fact, I think they have a special daylight savings time section on it. Other note is we have a recitation Monday, and this one is there are sustainability projects throughout the Fab Lab network. We're not going to try to cover all of them, but we'll look at a collaboration around the sustainable production of local hygiene solutions, and then work on sustainable development goals. So how everything we're doing here meets sustainability. So then with that, we have two very special faculty this week working with instructors Hank and Thorin. First, Tony, then Tom. So Tony was introduced to me by the U.S. National Institute of Standards as the U.S. leader in machining, the national expert in machining. Hand up. Let's see, there's a hand up and back down. Okay. Tony was introduced as the US's expert in advanced machining. There are a lot of experts, but so without trying to say the expert, he's one of the national experts in the US in machining. Let's see, Guillermo, do you have a hand raised? No. Tony ran an important machine tool research center. He's now working at one of the leading machine tool suppliers, so a world expert in machining. And so he's going to do metal. And then Tom Bodett, who's famous for many things, but what his real love is woodworking. And he runs a gorgeous woodworking space in Vermont. Gorgeous location, gorgeous wood, and gorgeous people all coming together. And so Tom is going to cover wood. And so with this great team, take it away, Tony.
Okay, thank you, Neil. I'm a distinguished technical fellow at MSC Industrial Supply Company, and today I'll be talking about CNC machining, CAM software, tooling, speeds and feeds, and work holding. My partner, Tom Bodett, will focus on woodworking topics to support your projects. Tom, go ahead.
Thank you, Tony. I'm going to share my screen here, and we'll get started. Let me get this where I want it, and full screen, please.
Yeah,
Computer.
Well, Tom gets it.
Full screen.
Well,
there
Tom,
we go.
Yeah. Oh, sorry, Tom. Okay, great.
Yeah, that's what I want to see. So this, Neil mentioned, I am a woodworker. I've worked in radio. I've written books. Done a lot of fun stuff with my life. The funnest thing I do is woodworking. I've done it all my life, no matter what else I was doing. And now it is my life. I founded Hatch Space, which is about right now about a 10,000 square foot woodworking school and community center in downtown Brattleboro, Vermont, where I am today. I'm not downtown, but I am in Vermont. Okay, I see what Hank, what you were saying about the slides being horizontal. I don't know why that's doing that, but it doesn't matter really. So why wood? Um, now, I am surrounded by wood all the time. Here as I'm sitting, in fact, if you look at this slide here in the lower right-hand corner, that is a barn frame that I made 23 years ago, all out of wood. This is the barn that I'm sitting in right now. I'm sitting about right there. And this was all made from local woods. This happens to be red oak and cherry, black cherry. And we made all these parts and pieces by hand and raised them up and made a building out of them. So why wood? It's locally sourced and it's sustainable if your forests are managed properly. It is ubiquitous, with exceptions, of course, around the globe. There are trees that you can make wood out of, and it is durable. It's one of the strongest building elements around. You'll see frame houses standing after cement houses have been flattened by earthquakes because wood is both strong and flexible. It's also extremely beautiful. This is some finer woodwork I've done over the years. This is a cradle that I made 23 years ago as well. That was a good year for me, for my son, who is away at college now, and a little box that I made for him out of these same mahogany planks. I love being around wood. Wood is a great roommate. It feels good to me to be in a room with wood in it. This is some things that I've made for my own home. An arts and crafts style cherry table I designed and built as a fir door, a slab walnut table, which is just a slab of wood right out of a tree, a couple little toothpick boxes out of the same wood. I love doing that, making multiple things out of one tree. And keeping them together. This is a little detail on that same walnut thing. These are handmade bow ties, they call them. It's a way to sort of knit a crack together as wood moves. Wood always moves. And then this is to show some of the artistic things, some of the variations that you can do with wood. It is infinitely variable. And so why I'm here is because when Neil visited Hatch Space 3 or so years ago, we were walking around. We walked into our CNC room where we have 2 CNCs, a 3D printer, we've got laser cutters, all of the things. And as we were talking about it, I confessed to Neil that I never used these things. And he said, why not? And I told him because I love making things with my hands, and when I make something on the CNC, or I have somebody else do it for me, more likely, it doesn't feel like making. So how did I get brought around to the light, as we say? This is an example of things I did by hand. This is that arts and crafts table. I cut all of these parts out by hand. Of course, I use power tools, but not computer guided ones. This is how I put the bow ties in that table with a chisel and a hammer. This is how I flatten that slab. What does this remind you of? It's a router on a track that moved back and forth, and I moved it down the table until it was flat, which is something that CNCs do just almost in their sleep, right? This is 3 renditions of a trophy that I was asked to do for a corporate entity that I worked for a long time, Motel 6. I did their advertising for them, and I volunteered one year to make their corporate awards, and they said, sure. So by hand, I made 3 variations on the theme, and they picked the most difficult one, and I said, great. And I said, how many do you want? And they said 36. And I thought, okay. So when you're a hand woodworker like I am, and you enjoy making things with your hands, so we usually just make one thing and then we make another thing. And so a CNC doesn't have a lot to offer if you're only going to make one of something, because there's a lot of work that you have to do before you turn that machine on to do it. But when time is a factor, it matters. I had a very little time, I think something like 6 weeks, to make 36 of these things before their annual convention.
Tom,
Yep.
1 minute left.
Say again?
You have 1 minute left.
Okay. So
Yeah.
I'm gonna talk more about that process. This is how I got to using a CNC machine, and on that project was my very first attempt at it, where I put it to great use. But where I ended up is, when the machine is done, you are not. So how did I get from this, which the CNC machine spit out in great order, to these beautiful handcrafted trophies that people took home and enjoyed. So I'm going to talk about that when I come back. Right now, Tony will tell you what goes into the machining process that produces pieces like you see in the left-hand photo. And like I say, when I come back, I'll talk about what comes after that. Thank you.
Okay, thank you, Tom. So as he mentioned, I'm going to talk about an introduction to machining. So in machining, we use a defined cutting edge in order to produce parts with the desired dimensions that we've defined digitally. Because machining removes material from the stock, it's a subtractive process. So this stands in contrast to additive processes that you might be familiar with, where we add material in order to reach a near net shape component. When we're performing machining operations, we remove material in the form of what we call chips, and they're sheared away by the cutting edge. So here's a little cartoon of what that cutting edge might look like. So it's a wedge-shaped component here, and it has two important surfaces. There's the rake face of the tool, where the chip slides over the tool as it's sheared away. And there's the flank or relief face of the tool, which is adjacent to the new surface that we just created. So depending on those angles of those surfaces, we have force, which is necessary to produce our chip. So here's another little schematic showing two very important force components when we're shearing away material. One is the cutting force, and that's the force that acts in the cutting speed direction. I'll talk more about what that means. And a second component is the thrust force. That tends to push the tool away from the surface that we just created. And so collectively, those define the force that the tool and workpiece must resist as we're creating these new surfaces. Now, because we have force, which is applied at some cutting speed, there is power, which is introduced by our machining operation. We can describe that power as either a power per unit volume of material that we remove, or the force, the cutting force per unit chip area, so the cross-sectional area of the chip that we're removing. And that's described by the width of the chip and the thickness of that chip, which we define when we set up our machining operations. So in the table here, you can see a collection of some metals and some woods that list this specific cutting force or specific cutting energy value. And we can see for the metals, it's like 1,000 to 5,000 newtons per millimeter squared is one set of units. And then for the woods, the materials you might be using in some of your projects, it's more like tens of newtons per millimeter squared. So the scale of the force is different, of course, but the activity of removing this material is very similar. Okay, because we have power, which is input into the process, we have an associated chip temperature increase. So things get hot when we remove this material, and the tool gets hot, and the chip gets hot, and to a lesser extent, the workpiece temperature increases. Now, what you'll see embedded in my slides here are some movies. I'm not going to play those here, but you can watch those later. Hank has uploaded these slides, so you can review that material afterwards, just saving time. Okay, because I'm removing material with high forces and temperatures and cutting speeds, tools eventually wear out. I like to say that machining is a competition between the tool and the workpiece, and spoiler alert, the workpiece always wins. So we have these wear features which are produced, and so periodically we change cutting tools as they get worn out. Think of the edge as becoming more dull, but there's also features on that edge which can cause it to fracture and damage your workpiece. So there's different tool materials that we can choose from. The two main categories are high-speed steel, which is an alloyed carbon steel, and carbide, which is actually tungsten carbide particles, which are bound together under pressure and heat by a cobalt binder. And so we can form tools in that way. We can also form cutting inserts. And so some of the carbide tools are solid carbide. Other carbide tools have steel bodies with inserts, the carbide inserts clamped to that steel body. So we only replace the inserts in those particular cutting tools. Now, in order to make the tools last longer, we can apply coatings to those tools, and there's lots of different coating alternatives. This shows some of the examples, but one of those that's very common is titanium nitride. You can recognize this coating by its gold color. So it reduces the friction between those cutting surfaces on the tool and the workpiece, and it's a high hardness coating, so it tends to extend the tool lifetime. Another way to extend the tool lifetime is with cutting fluids. So we can choose oils or emulsions or synthetics. Very common in metal, maybe not so common in woodworking, although you might use an air blast to clear the chips in your woodworking applications. Okay, so I just wanted to now talk about some of the machining operations. We'll focus on milling because that's the one you'll probably use most, but I wanted to touch on all of these applications. So the first is turning. In this case, we have a rotating workpiece, and then the tool moves past that rotating workpiece to produce axisymmetric or round shapes on a lathe. So the tool we use in that case is a lathe. It has a spindle that rotates the workpiece, and then a cross slide that moves the tool relative to that rotating workpiece. Here's a video you can watch. So here's some example turning applications, but what I wanted to point your attention to is the parameters that we specify when we generate a part program for our CNC machine tool. So for turning, we specify the depth of cut, so that's the difference in diameters divided by 2. The feed per revolution, so what's the advance of the tool per 1 revolution of the workpiece? The spindle speed, the rotating speed of the workpiece, and then the diameter that we've left behind. So that leads us to a term you might have heard, speeds and feeds, right? We always have to select these for machining operations. So here's how we calculate those for turning. Cutting speed specifically means the peripheral velocity of my rotating workpiece, and we labeled it here V, and so it's a product of the diameter of the workpiece and the rotation speed of that workpiece. The pi term there is to correct for rotations to radians. And then we also have the feed. So that talks about the linear feed rate of the tool past the workpiece. And it's different, of course, than the cutting speed. For turning, that's the product of the feed per revolution and the spindle speed that's rotating. Now we have cutting tools that we're going to select for turning operations, and this shows some of the geometry that we specify. For solid body tools at the top, and then indexable or inserted tools at the bottom. Now let's get on to milling. So in milling, we don't rotate the workpiece, we rotate the tool. And so the tool is rotating and we move it past our stock in order to produce the geometry that we've defined in our computer-aided design or CAD model. So there's different geometries for the machines, what we call mills, that carry out milling operations. On the right, there's a 3-axis vertical spindle milling machine. So by 3-axis, what we mean is there are 3 translating axes that we control with our part program in order to produce a desired geometry. Okay, so in the top center, that's what a milling machine might look like. That's a 3-axis computer numerically controlled milling machine. If we took all that guarding off, what we see is the inside, the casting and the table and the spindle carriage that provides the motions. And one thing that's important to understand is the motions that we command in our part program are carried out by DC motors that rotate a ball screw, generally, with a nut. That nut is fixed to the moving component. So that geometry that you see on the left is the castings and the components that enable us to perform those 3 linear motions. And then in the top right is something more similar to what you might be using in your projects, which is a CNC router. The geometry is different. This is a geometry with the spindle mounted on a cross rail, which is a gantry over the workpiece, which is moving in and out. But they're doing the same things in order to produce the components that we want. So we also have 4-axis milling machines where we've added a rotary axis. You can see the B axis, which has been added here. And then 5-axis milling machines where we've added 2 rotary axes. And we label those rotary axes based on which linear axis they're rotating about. So the A axis rotates about the X, the B axis rotates about Y, and the C axis rotates about Z. And so there's lots of configurations from which we can choose for our 5-axis milling machines. Now, at the business end of the milling machine, where we're producing our part geometry, we have a cutting tool, and there's some language around these cutting tools that it'll be good for you to understand. One is the cutting edges are sometimes called flutes and sometimes called teeth, depending on who you're talking to. And so we specify the number of teeth or flutes on that cutting tool. We also specify the geometry of the end of the tool. So it might be a square end, or it could be hemispherical, that we call a ball nose end mill, or something in between, where there's just a radius on the edge, and that we call a bull nose end mill. So for the ball nose and the bull nose end mill, that enables us to do contouring shapes where I can have any arbitrary shape that I might design that can be produced by our 3 or 5-axis milling machines. The square end mill is better suited to prismatic parts or maybe a roughing operation where I remove most of my material, and then a finishing operation where I get my final geometry. Within these operations, we specify the axial depth of cut. So that's the depth of cut along the tool axis, and the radial depth of cut. So that's the radial depth along the tool radius. And that can go up to the full radius of the tool, and we call that slotting. So this just shows, again, that we can have solid body end mills or indexable end mills where we clamp those little inserts onto a rotating tool body. Well, we have this tool that we want to rotate, so I have to get it connected to my spindle. So there's 2 connections that's necessary there. One is connecting the tool to a holder that clamps onto that tool. In your shops, that's probably going to be an ER collet type holder, where there's a flexible metal basket that the tool is inserted in, and then I use a collet nut to squeeze that basket within a taper, and that clamps around the periphery of the shank of the cutting tool. Another option is shown here, which is a thermal shrink fit, where I heat the tool holder up, it expands, I drop the tool in, and then as it cools, it clamps in the same way. Okay, and once I have the tool in the holder, I got to get the holder into the spindle. And 2 common methods to do that are just 2 different tapers. There's a longer taper called the CAT tool holders, and a shorter hollow taper called HSK. And both of these are widely used in the industry. Okay, so there's 2 different milling directions that we want to understand. One is called up or conventional milling, and one is called down or climb milling. So I have both examples shown here in the top left. The way I remember this is in up milling, my chip thickness is increasing or going up as the tool rotates through the material. So top left shows my chip thickness starts at 0 and then increases to my feed per tooth, also called the chip load, when I exit the cut for this 50% radial immersion. For down milling, on the other hand, I begin with the maximum chip thickness, which has the maximum force, and end with this near 0 chip thickness. And so for producing smooth surfaces, I often choose down milling because the force goes to nearly 0 as a tooth exits the cut. Now, again, we specify parameters for our cut in our software to generate a part program, and that's the feed per tooth or chip load, the spindle speed, the cutter diameter, and the number of teeth on that cutter. And from those, we can derive the cutting speed and our linear feed rate, or just the feed. In drilling, that's hole making. And so we can do that on a lathe and a milling machine. So there might be instances for joining components where you need to drill some holes. So that's possible on your milling machine by inserting the drill in the spindle. It rotates, and then I feed into the material. Sometimes in metal operations in particular, we want threads, so we can use threaded fasteners. And in that case, I can use a tap to cut threads into that hole that I just produced. In all instances, we also specify the speed and feed. So for every machining operation you're going to carry out, you will specify those parameters within your part program. So those are your decision. And I just included this slide because if this was kind of interesting, you might enjoy a couple of my books. These QR codes are for free download. I just want to share them widely, and I'd love to have them used in the community. Okay, now we're going to go back to Tom, and he's going to talk about finishing operations after you've done the CNC machining.
All right, thank you, Tony. And let me get back to my sideways. Come on. I want full screen. You see, I'm better at woodworking than almost everything else, especially this stuff. Okay, so we left off with my first project, the one that brought me into the fold. Were these, we made 40 of these 6s, knowing we'd probably blow up a few. And so the main thing is that everything that Tony just explained also applies to wood. If we're going to be making something big now, a lot of the times that's going to be furniture, because furniture is cool. It's useful. You can give it to your mom. You can take it home, put it in your apartment. And as I said in the beginning, it's beautiful. It's relatively affordable. And you gotta learn how to use it before you put it to one of these machines. So what I learned through this process was that a CNC is a tool like any other. It doesn't do, as I always used to say, the fun parts, why I stand and watch it. It actually turns out that it does the boring parts. And when it's done, the fun parts are all there for me. So you are in the toolpath as you go, probably more than you are with using other materials, because wood, you've got to prepare it, you've got to have it milled, you got to glue it up. In this case, if you're going to do something laminated, lay it out by hand the way you're going to want it to appear on the wood, and run a couple test pieces. You go through all of this and figure it out. And then there's a lot more to do. There's a lot of shaping and sanding and finishing and stuff that comes in. There is a video that I recorded separately. It's about a half-hour long, which talks a little more in depth about some of the basic woodworking techniques. And I would encourage you to watch that if you're going to be making your project out of wood. So a CNC is, like I say, is a machine, but it's also a computer. And like all computers, They're only as good as what you put into them, and a computer will do what you tell it to do, even if you didn't mean it. So you've got to be careful what you tell your machine to do with wood. And you can program your feeds and speeds for wood, but you've got to understand wood in order to make that work. Because the feed and speed up one side of the board ain't going to work on the other side of the board. So the reason is wood is weird. These two trees grew up in a similar forest, and look at this one is a beautiful straight grain piece of wood, and this one is twisted like a corkscrew. So imagine a plank sawn out of each one of those is going to act very differently. A good way to think of it is like a stack of straws. Imagine a stack of drinking straws all bundled together. You can twist them, you can fold them, you can bend them, you can smash them, but on their end, you can practically stand on it. It's very strong in that way. So the grain of wood is caused by a lot of different factors. Like I say in those pictures, what kind of tree is it? Where is it grown? What changed in its environment as it grew? There's a lot of things that will affect the grain in wood, which is essentially the direction of the growth rings that happen in wood. We all know that wood has these circular rings that sort of mark the passage of time. There's a light one and a dark one. The light one is the summer months. The dark one is usually the winter months, or when the growth is condensed. And grain is how wood talks to you. It's how it tells you what it needs. Here are some projects I just grabbed at random that show what the CNC can do with wood that is pretty clever and fun to work on. A joint like this, you could do that by hand, but you're going to spend a lot of time on it. A CNC, like I say, that'll do it while you leave the room. So understanding wood is important to avoid some of this. If you look at this as a random project I just pulled a picture of, where you have the milling process will grab chunks of the grain of this wood and blow it up. Here is an example. Tony showed you these bullnose routers, which is a round end thing. If you go too deep, or it's not sharp enough, or your speeds are too fast, it's going to tear up your grain. And this is, you see this grain here? That's the ends of those straws. So when you go through there turning your bit that way, it's going to start chewing on those things. It's going to look like that. And that's either going to ruin your project or make it very difficult to finish. Same thing happens with plywood. Plywood is a very good material for CNCs because it's uniform. It comes already flat and square. And it's kind of as plug and play as wood gets, but it's also wood, and it's got a very thin veneer on each side of it that will feather out. And then you have a problem where you put that into your chair and somebody's going to get a big splinter in their butt. And if you rub your hand along that, you're going to pick up splinters, or it's going to tear that edge back even further. So you want to avoid that. And also, it sometimes happens anyway, you have to clean it up. And that's what I talk about in the video. Here's another very common thing where you get tear out coming out of a dado cut, which is a very common CNC project. And you'll get this tear out at the end of the thing. So there's ways to accommodate that. Usually it's, again, feeds and speeds. Take less material, come out of that. You can go pretty fast through here. Make sure it slows down when you get to the end of it. And the other ways you avoid it is with the bit choices that, how am I doing for time, Hank? I am not looking.
You're doing fine. You have 3 minutes.
Oh, okay. Well, lots of time then. Well, let me, because I really rushed through some of this. So part of it is just imagine that this is all those stacks of straws. And if your bit is coming through there turning like this, it's going to tear at that point because this is very, very weak where these fibers are short. This problem was solved by using a different kind of bit. They were using an upcut bit that when it went around that corner, it's what an upcut bit does is it's clearing the chips upward. It's pulling up on that. And so it's putting stress right here on where these grains come out. And it's contributing to the stresses on that that the cutting is causing. And it was pulling that top off. That's also what causes feathering on that plywood. So in order to avoid that, you can use a downcut bit. And that's putting pressure down on those fibers. And then if you're going all the way through the bottom, you may want to put the upcut on for that final pass. Or there's also what's called a compression bit, which cuts one way at the top and the other way at the bottom. So if you're cutting a full sheet of plywood, you can run this down the end of it, and it will cut up on the down part of the sheet and down on the top part, and you can avoid a lot of that feathering and tear out. The danger with both the downcut and the compression is that it's not clearing its chips. If you're in a groove like this bit is shown here, all those chips are going to accumulate down in there, and they're going to heat up. And this is a compression bit, and there's no place. Those chips are actually colliding with each other and jamming up in there. And the thing about wood is it catches on fire. And this is a fire we had at Hatch Space not too long ago. It was our first and only fire, and it happened with a compression bit being used. The operator saw the smoke. He stopped the machine. He changed the operation, but it was already too late. A hot ember had been sucked into the dust bin on the dust collector, and it started a fire that we had to call the fire department to come address. And thankfully, the fire department is a block away and no real damage was done, but it was a great lesson learned. And so,
1 minute.
okay, so if you look at the video link, I'm going to talk in the video about choosing your materials and why to choose plywood, MDF, softwoods, hardwoods. There's exotic woods. There's some beautiful ones where some of you live. Grain direction, how to read it, how to accommodate it, and then some of the basic tools that you'll use. Because for me, when the machine is done, the fun begins. So now Tony will provide an overview of the CNC and CAM topic, and when I come back, we'll talk about putting all this stuff together. Take it away, Tony.
Sorry about that. Thank you, Tom. Okay, let's talk a bit more detail about this notion of CNC and CAM. So here's the basic steps that we follow to use a CNC machine to produce a part. We first have to design that part. We're going to have a digital version of the thing that we want to produce. And so we do that in computer-aided design software, or CAD. We then take that CAD model, upload it into our computer-aided manufacturing, or CAM software. The purpose of that software is to generate the instructions, or what we call the toolpath, for the CNC machine to produce the part geometry that we designed. That CNC part program includes the toolpath, the motions, and other machine instructions, and we upload that to the CNC controller. So there's a brain for the CNC machine. We give the brain our instructions, and then it proceeds in carrying out those instructions. Now we have a machined part that we can inspect or finish, as Tom's talked about. Okay, so this top right graphic shows what a CNC part program might look like. It's a number of commands, and those commands are in this language that we call M and G code. Now, if you ask Neil about M and G code, he might say, let's get rid of that entirely, but that's a separate conversation that we can have. So these M and G codes have specific meanings within this program that we upload to our controller for the machine. Let's take G01, for example. That means I'm telling the machine to do a linear interpolation from one location where I am right now to a new XY or XYZ location, which is somewhere else. So I have to tell it the feed rate to move between here and there, the tool that's going to be in the spindle that's rotating at some spindle speed. So all of that information is embedded in that single G01 command, which is on one line of our part program. So we have this part program that's going to produce this geometry that we want from something. That something could be a prismatic block, a block of material, or a piece of plywood, or it could be something more complicated, like a forging or a casting or an additively manufactured component. But in any case, once we've used our CAM software to generate this part program, we upload it into our controller, and your machine will have its own controller. They're not all made by the same company, and so you have to tailor your part program to that machine. We call that post-processing. And so the language that you might hear in the shop is, oh, you need to post your part program to that machine. And when you do that post-processing, it tells it the geometry of that machine and some other details about the controller. Okay, so here's a list of some of the common M codes that might be embedded in a part program, like turning the spindle on, the M3 code, stopping the spindle, the M5, and then turning coolant on and off if we wanted to use coolant. Another thing we can do is group a bunch of commands together so that we don't have to program each one of those individually. So I talked about hole making a little bit, where we have a rotating drill in the spindle, which is forced into the material to produce a hole. Now we need to clear those chips, just like Tom just mentioned. And so we can use something called a peck or pecking cycle, where I'm encroaching into the material to produce the hole. I retract to clear chips. I go a little deeper, and so on. And so that's called a pecking operation to produce deep holes. So I can define that pecking operation simply by this G83 command, but embedded within that macro that we call it, maybe 20 or more lines of code. So it just simplifies programming. This is what a part program might look like that your CAM software produces. So I have some initial comments to start the CNC program. Then I load the tool that I want. That's the T1, meaning I want the tool that's in pocket 1 of my tool holder to be inserted into the spindle. Then I turn the spindle on at a specified spindle speed. Here it's 9,200 RPM, specified by that S command. Then I turn coolant on, in this case, maybe not for wood, and then move to a position above my part. That's very common. I move to a safe position above my part, and then I move down and start removing material with the rest of my commands that tell that tool where to move through three-dimensional space. And then at the end of the program, I turn the coolant off, I turn the spindle off, I retract the tool, I move back to that safe location so I'm not going to bump into the part, and then I end the CNC program. So there's other things that we have to consider when generating this part program within the CAM software. Well, I got to hold that part some way, right? So work holding considerations are important. And in fact, the model of how I'm holding that part is usually included in our CAM software so I don't have collisions. If I'm holding a part by a vise and I don't have the vise in my program, I might have an approach direction that runs right through that vise to get to my part. So I want to have that included in the CAM software. Closely related to that is something we call the work coordinate system. That tells me where the part is located in the machine's 3D space. So I assign a location on the part and I say, this is the origin for the part, and then I'm going to program my motions relative to that local origin, which generally is different than the machine tool's origin, where it thinks it's at its 0, 0, 0 origin location. So we get the difference between the machine home location and the part origin by something we call work offsets. And so usually there will be a table of work offsets that tells the machine, this is where my part is in your coordinate system, so it knows how to move around. The first of those work offsets is another one of these G commands, which is G54. When I have other parts, I start just adding one. So G55, G56, and so on. Here's some videos that you can watch. Okay, so now we have our part located in space. We're going to start moving around to remove material. We want to have these safe heights that I'm going to move from. So that's what you see in the top left, is these planes that we define where we rapidly move to that plane, and then I'm going to have feed motions down to my workpiece and start removing material. That's just to keep things safe so I don't crash my machine. Also within my CAM software, I have to specify my feeds and speeds that we talked about. In milling, these often take the form of the axial depth of cut, sometimes called the step down, the radial depth of cut, called the step over. So think about enlarging a pocket. So I'm stepping over each time to make that pocket bigger. The spindle speed and the feed per tooth, also called the chip load. And then, of course, I have to specify my feed in and feed out motions. Within my CAM software, I have to tell it what tools am I going to use. So I have a tool list that lists the attributes of the tools that I've selected, and I will sequentially grab those tools, perform a machining operation, and then continue. What you see in the picture here is something we call a face mill. That's a larger diameter tool that's really good at making flat surfaces. Now, one thing that we won't talk a lot about here, but I want you to understand is that when I've selected a machine, holder, tool, workpiece combination, I've defined a dynamic system, and it will vibrate with the cutting forces that are necessary to shear away that material. And the parameters that I select in my CAM program are related to the vibration characteristics of my setup. I've provided an example here. Hank has uploaded these files for a full CAM instructional tutorial. There's a PowerPoint, there's a Fusion file, there's setup sheets, and there's videos to show the animations. So I will stop there. We're going to return to Tom, and Tom is going to continue with a description of joining and fastening. You're muted, Tom.
Thank you, Tony. So let me get back to. It keeps moving on me. There we go. All right. So the next project that we put to work at Hatchspace, put our CNCs to work at Hatchspace, was this one. We had a local museum who asked us to make some new display cases for their new, they were moving to a new space, and they were adding 20 display cases. So we went back and forth, and with one of our people kept doing renditions with the CAD software, and we came up with a very elegant design, very appropriate to our area. It's kind of a shaker style piece of furniture with these arched tops, arched aprons, and excuse me, and we did a 3D CAD rendition of it. We decided that we would use black cherry for this because it's a beautiful wood. It's also a very, very millable wood. It's a very agreeable hardwood to work with. A lot of furniture is made out of cherry, particularly in New England. So a simple thing. The project was we had to make 20 of these. They had to be mortise and tenon fit. They had to have slots all around these in order to hold the display glass. The top had to be removable, and everything locked together. And we made the decision that we wanted no visible fastenings on it, which is, again, a kind of a traditional shaker thing. So that was the project, and it's 20 of these means, like, we've got 4 legs on each one. Each leg was going to take 1, 2, 3, 4 mortises. It was going to have 2 rabbets for the glass, and it was going to be tapered on 2 sides of it. And that had to be done 80 times. And so every piece in this had multiples of 20. Now, front and back, those are identical, so we had to do 40 of those. The sides, those are identical, 40 of those, and on and on. So what we did, and I say we pretty liberally, what Rowan, our operations director, did, he set up these wonderful jigs on the CNC, using the CNC, and on a piece of MDF, he made holders for the sized components, and we used the CNC. These here are the rabbets that hold the bottom in place. Here is more of that. This was all done in one operation for the aprons, where they did the rabbets, and then, as Tony described, where you can change the tool. One of our CNC machines has an automated tool changer, our Phantom. And so it did the rabbets, and then it went over to the tool changer, and it grabbed a different tool, which then cut the circles in it, and then later on we even added a third step. Like, these are the legs, so we had to taper those legs with one cutter. We had to make the mortises with another, and then we had to make these rabbets for these dados, let me say, for the glass with another. But that was all done on the CNC machine. All we had to do was, after it was done with one side, to turn it and let it do the other side. And at the end of it, we had like, there's the legs being done. You can see the tapers on these legs were already done on a different tool. Then when they were done, we had some help. This is one of our interns who they have a little hand router there that's just using to round over the corners, all the sharp corners that the machine left. And then I personally, because I love it, I sanded all of these parts. And I started with a grit of probably 180, and I went to 240, and I went to 320. I cleaned up all of the edges. I cleaned up any spurs or splinters that might have been left in the rabbets. And when I was done for assembly, they were ready for finishing. The machine did a really good job. There wasn't a lot of machine marks to clean up. I once heard woodworking described as every tool you use is to clean up the marks that the tool that came before left for you. And that's true from the time you cut that tree down until you start putting it together. And this is the finished product. This is in the museum. They turned out beautifully. The client could not have been happier with it. We did make one compromise on the fastenings. They needed these tops to be able to open so that they could, of course, arrange their displays and change them when needed, but they didn't need them to open a lot. So rather than come up with an elaborate hinging and locking mechanism, we screwed the corners down with safety screws, which are those screws that you can screw in, but you need a special screwdriver to unscrew. And they were quite happy with that. They're a real showpiece for them, and it's a real showpiece for, of course, Hatch Space and our community too, because we were able to do this at about half of what they would have paid on the market for those. And so there's 1,000 different joints at least, and I'm just going to cover a couple of the basic ones here, and I encourage you to look up wood joints on the internet. I didn't want to use up a lot of our time here showing you things that you can easily find on your own screens at home. This is the basic mortise and tenon, and this is what would be the classic joint for a piece of furniture like that. You dig a mortise in one side and you make a tenon in the other. The fit is where the strength comes from, and of course the glue. And there are also dowel joints, which work somewhat the same way. You'll see this a lot in older furniture because they're easy to make with just a drill. Dowels are just these round pieces of wood. You drill a receiving hole and one for the tenon, and then you fit them together. A combined mortise and tenon and a dowel joint are very strong. You can make furniture without any glue or fastenings at all using dowels like this. This tenon on this piece came in here, and they drilled dowels through both pieces. You hammer these in, and with a tight fit, and that piece of furniture will hold together without any additional fastenings. We did not use traditional tenons. There were too many of them. Each of those cases, I think, had 16 or 18 tenons. It was far too much to do. So we used what's called a floating tenon. This is a tool called a domino joiner. There are variations that the Festool makes this. There are variations of this, but what a floating tenon is it's kind of it's like a dowel, only it's a piece of flat wood, usually with the edges rounded over. So you make a round-cornered mortise in your piece, and we did the tables. We did the ends of these tables with the mortiser because it was easier than setting that up. The CNC does not do the horizontal cuttings very well. Yeah.
1 minute.
1 minute. Okay, great. Dovetails, that's another one. Again, look it up. That CNC will do a dovetail joint. This is a nap joint, very tricky. I've never made one. I'd like to. And then I left a link here, and Hank's going to put that in the chat, that shows a whole, there's a whole company, or there's a company out there that you can download the software to make some really complicated, beautiful Japanese joinery on the CNC. And I would encourage you to go look at that. So fastenings, how are you going to put this stuff together? Very quickly. Glue is a fastening. If you have good joints and when you're working with wood, often glue is the only thing you need. There's a lot of different kinds. These Titebond original, Titebond 2 and Titebond 3 are universal. They're called PVA glues, polyvinyl acetate. They're very good. The original is just for interior. Titebond 2 is moisture resistant. Titebond 3 is basically moisture proof. The other choice is epoxy. Again, there's other things, but basically PVA glue or epoxy. Epoxy is stronger than PVA. It also works well for gap filling. If you do have loose joints, you can use epoxy, and it will fill those joints very well. Other ways to put things together, of course, are screws. Screws. There's 1,000 different kinds of screws. This is a self-tapping modern screw here that are very, very easy to use. They're available everywhere. And then this is like the classic wood screw. They're also beautiful and they hold very well. but they're not used very much anymore unless you're really trying to look classic.
-1.
Okay, and then there's knockdown bolts and plugs. If you've ever put together a piece of IKEA furniture, you know what those are. And one last thing, and I'm sorry I went a couple minutes over, but once your project is put together, put your hands on it and decide where you're going to leave a little piece of your heart. And that's when the finishing comes in, and that's when the real chef's kiss of that piece of work that you made comes into play. Thank you very much, and Tony, it's all yours.
Great, thank you, Tom. Okay, so Tom mentioned how he enjoys sanding. I spent a summer working in a cabinet shop where my entire job was sanding, 8 hours a day for 3 months, and I was cured. I no longer enjoy sanding, but Tom and I can split that activity. Okay, so I want to elaborate on some topics that I've discussed in previous sections. The first, we've talked about speeds and feeds as the decisions that you make as a programmer in your CAM software. And so I just wanted to show you, here's the equations that we use to calculate between cutting speed and spindle speed, for example, and linear feed rate and feed per tooth or chip load. So we make these decisions, we program them, and then we see the outcome when we execute our toolpath on a CNC machine tool. So where do we get these numbers? How do you make these decisions? One resource is cutting tool manufacturers. So they will provide tables based on a tool that you select and the work material that you want to remove material from. So in this table you see on the right is a number of different metals. There are also tables for woods, of course, and a parameter that you might see is SFM. So you say, what does that mean? Well, it's the unfortunate continued use of English or empirical units as a cutting speed or surface velocity of your tool of surface feet per minute. So that's what SFM means. And that just means cutting speed. And so I can use a table like this where I combine my tool with my work material to have a recommendation for my cutting speed. Those tables often also include my chip load or my feed per tooth value. And so I can look those two things up, and then I can use those to guide my programming in my CAM software. One caution that I want to give you is these tables are sort of generic. They're not specific to your setup. And in particular, they don't know about the vibration characteristics of your setup. So you want to try to make your setup stiff with your work holding that we'll talk more about, and your tool selection. I don't want to stick my tool out any more than I have to, because the longer it is, the more flexible that cantilever beam becomes. But these provide a good starting point. They might not work every time, but they're a good general solution. So here's just some numerical examples of if I have an aluminum workpiece, for example, and I've chosen a 1/2-inch diameter carbide end mill. This table recommends a cutting speed of 800 surface feet per minute and a feed per tooth or chip load of 5.5 thousandths of an inch. So from those numbers, I can calculate my spindle speed. And then if I know I have 3 cutting edges or 3 teeth on that end mill, I can get my feed rate, my linear feed rate. So there's my speeds and feeds that I need to make decisions. So what if I had that same end mill, but now I'm machining a stainless steel instead of aluminum? Well, my parameters change because stainless steel is a harder to machine material. It takes more energy to produce that chip. I'm going to have a lower cutting speed so that my tool doesn't wear out too soon. So now my cutting speed has been reduced dramatically down to 130 surface feet per minute from this table's recommendation, and my feed per tooth is reduced. The feed per tooth goes to the cutting force, and so if I have a harder to machine material and a higher specific energy, I have much higher force, so I can reduce my chip load in companion to not break my tool. There's online calculators which are available. I provided a couple of links in here. Machining Doctor there's lots of information on that website. And then a second one is specific to wood. Okay, work holding. I've listed a few here that I want to take a look at that you might see in your lab. The first of those is a vise. A vise is terrific for holding prismatic parts. So there's two clamping edges that I bring together and squeeze that part. So a companion product that I often use is something called parallels. So that's two hard steel parts which have the same height, and I put them in my vise, and that can raise my workpiece higher from my table. So often you'll use a combination of parallels and a vise. Work stops are also common. When I have multiple times I'm going to be putting a part in a vise, I can locate the part in the vise automatically or manually, but pushing it against this work stop. Soft jaws can be very useful. So if I have a non-prismatic part, how can I clamp it in a vise? Say it's round. Well, I can produce these soft jaws. I can machine them separately to have a round shape so that I'm clamping around the edge, the surface of that round part. So these soft jaws are produced in another operation and then used to clamp my specific geometry. Toe clamps are very common, so I just have a threaded connection, and then I'm bolting this toe clamp down on top of my part to hold it flat against the table. Lots of configurations of the toe clamps are available. V-blocks can be useful. If I have a round part, how do I hold that thing horizontally? Well, if I have a V shape, I can lay that round part in the V shape and then clamp down on the part within the V-block. I can also put different angles on my part by clamping it to put it at an angle in the V block and then still machining with a vertical spindle. Vacuum plates are very useful, particularly for large pieces of plywood, for example, that you might be machining on. So I can have a large flat surface. I draw a vacuum through that surface, and then by putting a board on top of it, it squeezes that board against the surface and holds it in place. It doesn't have to be flat. There are also vacuum fixtures that have a particular shape, and so I can clamp the shape onto my fixture with the companion shape. Very common in aerospace applications.
Only 1 minute left.
Another way to hold large plates is by tabbing your parts. So I will machine the thing that I want, but leave a little tab of material that I can release later. Very helpful in a lot of woodworking instances. Now, I talked about the work coordinate system a bit. What I wanted to tell you here is sometimes we have to turn the part over. And so I can use a work coordinate system based on a feature in order to register my part when I turn it over. So for this example, I might machine the top of this component, and it has some holes in it. Once I've produced those holes, I can assign a coordinate system to that hole, and then on my machine, probe the hole so I know where it is, and then have my machining operations for the backside based on that hole. We call these ops when I have to relocate a part. So op 10 and op 20 means front and back of this component. I already mentioned that the machine has a work coordinate system. It has an origin or a home position, but my part is located somewhere on the machine, and that's my work coordinate system. And so again, we use this G54 table in order to tell the machine, here's where my part origin is relative to what you know to be your machine coordinates. Then we can program in the work coordinate system, which many times is much more convenient than using the overall machine coordinate system. And if I have multiple parts, maybe I have a large board and I want to have repeated features like the sixes that Tom showed us, I can have a coordinate system assigned to each one of those. And I just add to my G54 table in that case. Okay, we've covered our material now, and we're ready to return to Hank for your project.
Okay. So for the group assignment, do you see my screen?
It's zoomed in too close. We see just a little bit of it.
It's strange. Okay, anyway,
Good now.
that's good now. So this group assignment, do your labs safety training, test all the different elements of your machine. So the runout, alignment, fixturing, speed, feeds, materials, and the toolpath for your machines. And then as an individual assignment, make, so design, build, and assemble something big.
I think we still see 1/4 of your screen, Hank.
Is this better?
No, it's just we see only just a part of your screen for some reason.
Okay, now it's good, Hank.
Anyway, you have to make something meter scale for extra credits. Don't use fasteners or glue. So work again with a specific construction. Include curved surfaces or use a 3-axis toolpath.
Hank, let me take over just for a minute at the end.
Yeah, that's up to you.
Yeah. So let's see, that should be back. Okay. So first note, so yeah, actually I'll wrap up with the others, but safety. These machines, so first inspiration, you'll have a large format machine tool. Standard is you get in English units a 4x8 sheet of plywood and you make something big, furniture, laptop stand, bookcase. One of the best projects done in this class was Sam made this gorgeous kayak, was his homework for inspiration. Safety is critical. You can get cut, burned, impacted. You saw an example of fires, tools can break. So a tragic thing that happened a few years ago was a Yale student died when her hair got caught in the lathe. So to do this week's assignment, anything making chips, you wear safety glasses, you wear shoes to protect your feet, hair is tied back, no loose clothes. Look, listen, smell. You need to listen to what it sounds like. The machine will scream when it's unhappy. In woodworking, you'll smell it when it's unhappy. Your hand isn't a tool. You never reach into a powered tool. You always ask, what's the emergency stop before you turn it on? If something goes wrong, you can panic. You want to make sure you know how to turn it off. You always do it with somebody else with you. And you don't do it in the middle of the night. You don't do it tired. You don't do it when you're mad. You need to be in a Zen-like state to machine. The machines can hurt you. You can hurt them. The safety training is essential this week. Yeah, it was a whole boat was made for the homework. The group assignment is run out is if the tool isn't quite aligned, the size of the cut is bigger than the tool. Kerf is what gets left as the tool goes by. Alignment is how square is your machine. Fixturing is how you hold it down. For plywood, very often we use, we pop in with a cordless screws, and they're ones that are composite ones that you can machine right through. You need to go through what are the speeds and feeds, what are the materials you're using. Ted, hand up. No. And so that's to characterize your machine, go through the safety training, and then make something big. The non-flat is you can, this is what I'm showing in the upper left is called kerfing. Below that's called flexures. You can start with sheet stock, and with those techniques, you can make something that has curves and it's not just flat. This is a very liberating and a very creative class. You should come out empowered. You can make things on the size of the environment around you. You're going to be very limited by machining time. So don't be heroic in the design work. Give yourself a day or so on design work, a day or so on basic training, and then what's rate limiting is going to be sufficient machine time and then time for post-processing. For wood, you can spend hundreds of dollars on beautiful plywood. Most likely you'll be using oriented strand board, OSB, that's sort of like hot dogs or sausages of wood. It's the little bits left over smushed together. It's cheap and it's used for like boarding up buildings, but you can actually do beautiful finishing of OSB. When you're done, you can machine and sand it as a note. So careful time management, careful safety training. And with that, this is a very liberating week. You're going to make big things. This might be my favorite assignment. It's make something big. So sustainability, so global open time on the weekend, sustainability, recitation. I'll be eager to see what you do for making something big. And Tom, Tony, Hank, Tharin, I think you may get the prize for great preparation and great choreography of a session. It was a pleasure to listen to you.
Oh, thank you.
Thank you.
And with that, we're done. Happy machining. I'm eager to see what you make.
Thanks, everybody. Good luck.
Bye-bye.
Yes.
Ciao, nos vemos.
Bye.
Tschüss.
Ciao, grazie.